Welcome back. So in today's video, I want us to look at question number 10, and this has been adopted from the IEB past paper for 2015. Okay. So they say that in the diagram below, we have a solid white circular cone, right, which is centered within a hemispherical container, right? So you can see that we have a cone, right, which has basically been inscribed inside of a hemispherical container, right? And we're told that the radius of this hemisphere is 5.3 centimeters, okay? And there's this statement over here that says, of all possible white circular cones that can fit inside of the hemisphere, calculate showing your working the value of x, which we must, x is going to represent the height of the cone in centimeters, right? For which the cone, right, will have a maximum volume, right? And we need to call the radius of our cone P, right? We'll put all of these details on our diagram shortly, right? Just going back to this statement that says of all possible right angle cones, right? What they're basically meaning is that if you can see over here with my sketches, right, you can inscribe a cone in this hemispherical container, right, which could be like this, right? So you can choose your base, okay, to be these 2 points over here, right? And then you'll have sort of like a medium fat cone like this. Or you can choose the vertices of your base to be even lower down the container, and then you'll have even more of a wider cone, right? Like this. Or you could even choose the vertices, right, to be almost right at the top, right? And your cone will be skinnier, like this one. Okay? So what we need to find, okay, is the x value, right, the height of the cone, which will give it its maximum volume, right? So what height must this cone have so that when it's inscribed inside of this hemisphere, right, it has the maximum volume? Because you can see there's different scenarios of these cones, right, and each of them have a different volume. Right, so I've redrawn our situation and I've put in the variables that they wanted us to work with, right? So they wanted us to call the height of this cone x, okay? So x is the height of the cone, right? And they wanted us to let the radius of the cone be p centimeters, right? And I've indicated that over there, right, with the letter p. Can't really see it so clearly, but I've written a p over there, right? And something else that they gave us is that the radius, okay, of this hemisphere is 5.3, okay? We can put that in, right? So the center of this hemisphere is at the apex of this cone, right? So from the center to the circumference, that is 5 square root 3, right? That's the radius of the hemisphere, right? But notice again that this radius can move around, right, the entire circumference of this hemisphere. So it would be necessary to label a useful radius. So a useful radius is going to be the slant height, right, of our cone. Okay, so this slant height is of a value 5 square root of 3, right? Now you can see when you put in that slant height, it should be more evident to you now that you actually have a right-angled triangle, right? So the cross-section of this cone, right, is made up of a height x, a radius p, and a slant height of 5 root 3. Okay. Now we go back to our question and we see that what they want us to do, okay, is to find the maximum volume of the cone, right? So which cone will have a maximum volume, right? So our optimization equation is the volume of the cone, right? And we're given over here that the volume of a right circular cone is given by this expression, right? So 1/3 pi r squared times h, okay? We're going to have to modify this expression a little bit so that we work with the variables that they gave us, right? So I'm going to call the volume of the cone VC, right? And this is going to be equals to 1/3 pi, right, times its radius is P, so P squared, right, times its height, and its height is represented by x in our situation. Okay. So this over here is our optimization equation. And you can see that the problem right now is the fact that our optimization equation is in terms of two variables. Okay, we have a variable p and we also have a variable x, right? And we saw in the beginning that changing this variable x essentially will change the volume of the inscribed cone and also its shape, right? So now we need to find the x value that will give us the maximum volume of this cone, right? So which means that we need a constraint equation, right? And the constraint equation, right, is going to be very simply given to us through the use of Pythagoras in this right angle triangle, right? So in this right angle triangle, we know that that right angle triangle must obey the rule of Pythagoras that says that x squared, right, plus p squared must equal 5 root 3 squared. Okay, so because it's a right angle triangle, it has no choice. It has to follow Pythagoras' statement. Right. So this is going to become our constraint equation. Right. We can work with this constraint equation to solve for either x or p, right, and then substitute one of those variables into our optimization equation in order to reduce it down to only one variable. Okay. So you can see that the easiest thing to do is then to solve this constraint equation for p squared, since we have a variable p squared in our optimization equation. So doing that, we'll have that p squared, right, is equals to, well, 5 squared is 25, and 25 times 3, that is 75, okay, minus, right, x squared. Okay, so we can call this equation 1, right? Then we're going to say substitute equation 1 into the optimization equation, right? And when we do that, we will then change the optimization equation to be that the volume of the cone, right, is going to be equals to 1/3 times pi times p squared, which is 75 minus x squared, right, times x. Okay, then we can distribute this x into the bracket, right, together with distributing this 1/3 pi into the bracket as well. This will then allow us to write this as v of x, because now we have the volume of the cone in terms of the variable x, right? So v of x is going to be equals to 25 pi x, right? And that comes from 1/3 times, 1/3 pi times 75 times x, right? Then you're going to have minus 1/3 pi times x cubed, right? Now you can see that our optimization equation has now been transformed to have only one variable. Okay? And also notice that your optimization equation is a cubic function, right? So it's going to be necessary for us to be careful about which stationary point we are obtaining, because we want a stationary point that will give us the maximum volume, right? So working from now this new equation of the volume of the cone, right, in order for us to find its critical points, we need to take its derivative, right? So v prime of x, right? And note, when you are working with this, pi is a constant, right? It's not a variable. A lot of students mistake pi to be a variable, and then they think that they can't differentiate this. You can. Remember, pi is just a value 3.14 something something, right? So when you apply the power rule to this, okay, you are simply going to get that f prime of x is equals to, remember there's an exponent of 1 here, so 1 times 25 pi times x to the exponent 1 minus 1, which is just going to be 25 pi, right? Then over here you're going to have minus 1/3 times 3 is going to be 1, right? Times pi times x to the exponent 3 minus 1, which is x squared, right? So then you're going to have minus pi x squared. Now we have our v prime, or our derivative function, right? We can rearrange this and write this as v prime of x is equals to, right? I can take out a common factor of negative pi, right? And when I do that, I'll be left with x squared minus 25, right? So we can see now that inside of the bracket we have a difference of 2 squares, right? And we can work with that very nicely, right? So we're now going to go ahead and set v prime of x equal to 0, right? This will allow us to get our critical points firstly. Okay, so 0 is equals to negative pi times, if you factorize this, it's x plus 5, x minus 5. Okay, so they're dividing both sides by negative pi is just giving us that 0 is equals to x plus 5 times x plus 5, sorry, x minus 5. So then we have critical points, right? Remember these are currently critical points at x is equals to 5 and at x is equals to negative 5, right? So what we do with these critical points is that we then put them on a derivative number line, right? And this is going to help us to get our intervals of increase and decrease, right? So we have negative 5 and we have positive 5. These need to be then substituted back into our v prime formula, and the easiest v prime formula that we have is this one over here. So you can see I've now inserted the v prime formula into the calculator, so that's 25 pi minus pi times x squared, right? We are then going to choose test values within each interval, right? And that's going to give us the gradient of tangent lines within each interval, which also tells us whether our original function v of x, right, is increasing or decreasing in that interval, right? So for this open interval from negative infinity to minus 5, let's choose a test value of minus 8. Okay, and we see that we get a negative result, right? And for the interval between minus 5 and positive 5, let's choose a test value of 0. Okay, you can see we get a positive result, right? And for the last open interval from positive 5 to positive infinity, right, let's choose a test value of, say, 12. Okay, and we see we get a negative result, right? So what we were able to find is that we have negative 8, we have 0, we have positive 12, and we saw that over here the gradients are negative, right? And in this interval we have positive gradients, right? And in this interval we have negative gradients again, right? So our original function v of x, right, so the function that is mapping the volume of this inscribed cone, right, is decreasing to the left of the critical point of minus 5, right, so it's decreasing, right? And at minus 5, since that's a stationary point, the gradient of the tangent line is 0, right? Between the two stationary points, the v of x function is increasing, right? At the stationary point of positive 5, the gradient of the tangent line is 0, right? And lastly, for the last interval from positive 5 to positive infinity, your v of x function is again decreasing, right? So we see that at negative 5, okay, we have a local min, and at positive 5, okay, we have a local max, right, which is what we are after. So this is our point of interest, x equal 5, right? Okay, so when we go back to the question, you can see that they wanted us to show our working, right, and calculate the value of x, right? So they don't want us to tell us what the maximum volume is. They just wanted us to calculate the value of x that will give you the maximum volume, right? And we just did that. We see that that is going to happen at an x value of positive 5. So we can conclude this by saying, by the first derivative test, x is equal to positive 5 is a local maximum, right? So therefore the height, okay, of our inscribed cone, because x, remember, is representing the height of the inscribed cone, right? So the height that gives maximum volume is, okay, a height of 5 centimeters. Okay, right, so that will then be the end of that question, right? If they did, right, ask what is the maximum volume, right? What is the maximum volume of the cone, right? Then you would basically be working out the V of 5, okay? So you would take this x value of 5, which you know is what's going to give you the maximum volume. They didn't ask us to do that, right? But I'm just saying that if they did, you would take this value of 5 and substitute it back into your V of x formula. Just for interest's sake, let's just do it. Okay, so our V of x formula is 25 pi times x, and x must be 5, minus 1/3 pi times x cubed, right? And that will give us a maximum volume of the cone, right, as 261.799, right? If you had to write this to 2 decimal places, it would be 261.80, right, centimeters cubed. Something else that they could ask, but this is really just an interest question for myself, is what percentage, right, in terms of volume, okay, is this cone taking up? That would just be, well, what percentage of cone, right, is in the hemisphere, okay, and that would equal, well, the volume of the cone at its maximum position, which we just calculated, is 261.80, right? That will be divided by the total volume of our container, and we can get that, right, by using the volume of the sphere divided by 2. Okay, we get that the volume of this hemisphere is actually 1000 360.50 centimeters cubed, right? So 5360.30, sorry, 0.35, okay? That we can then times by 100, okay? And we see that the cone is only taking up by volume, right? Only 19.25% of the volume of the hemisphere. Okay. So 19.24%. Okay. That's it for today's video. I'll see you guys next time.